Welcome all of you for today's live session, week 4 live session for Economic Operations and Control of Power System course. Let us begin today's session. Today's session is a very important session because we are going to discuss two very basic operational problems. Power system operation problem. One is economic dispatch, another UC. Let me first introduce myself. I'm Gagan Meena, and I am a fourth year PhD student in Power System and Power Electronics group at IIT Bombay. So this will be the agenda for the live session, which we have been following for previous 3 live session as well. We will go through the overview of week 4 and then we will discuss some questions related to week 4, and in between we may also discuss some of the topics regarding that relevant question, if some relevant topic need to be discussed. Today I may shift a little bit from this agenda because I will start with one problem for explaining the ED problem, the economic dispatch. I will explain that using a problem. We will solve that problem and for discussing economic dispatch. Just to remind all of you that deadline for assignment 5 is August 28th. So please submit the assignment before time. And I hope all of you are able to access the recordings of live session as well as the material, the PDF, the presentation which I am using, that is available in PDF format on the web portal. On the left hand, I think on the bottom of left bottom, you will find problem solving session tab. Problem solving session tab. And there you will find a link for the Google Drive where you will find all these recordings, the link for recordings as well as for the PDFs. I hope these live sessions are beneficial for you and you are getting something out of these live sessions. Let us begin with the overview of week 4. Week 4, as I have already mentioned, that today, this week 4, the main content is the discussion about two power system planning problems, about two power system planning problems. One of them is economic dispatch. Right, this we have already discussed previously with losses and without losses also. And second is unit commitment. The only thing which we are changing here is, although we have discussed economic dispatch previously with and without losses for a particular demand to be met using different methods, but here today we are going to change the method. Here you'll see in economic dispatch we have already gone through different methods like equal incremental cost, what we call lambda iteration method. Then we have also seen this gradient descent. we find the gradient of the Lagrange function, and then we update the variables. Then we also saw modified gradient method to improve the convergence. We make one dependent variable out and then just reduce the size of the problem by two variables by removing lambda as well as the one of the generation. So if there are three generators, then the variables will be only two generators, P1 and P2, and P3 will be written in the form in terms of P1, P2, and demand. It becomes an unconstrained optimization in modified gradient. Then we saw the Newton's method, where we got the correct or the exact correction factor or the step size, correct step for the update, for updating, for updation, that we have seen in Newton's method by using the Hessian matrix. We did all that. Today we are introducing one more method, which is the new method, which is the dynamic programming method for solving economic dispatch as well as the unit commitment problem. For unit commitment, we will see the difference between economic dispatch as well as the unit commitment. And for unit commitment also, we will see different methods. Two of them are listed here, but there are other methods as well. So that we will see. So today's class is going to be very important from power system operations point of view. These two are the most simplest version of economic dispatch we have studied in the previous classes, with and without losses for a single time step. For a single time step, and that with losses, with network losses, and without network losses. Here we saw different ways to incorporate losses. One was B loss matrix, using B loss matrix. We can use historical loss data. B loss formula with same instead of matrix. On this thing, we can also use the Newton's, the power flow equations. Calculate losses. Power flow formulations. So all these things we have seen. This is single time step. Same economic dispatch can be done for multi-time step. We will see why do we need to go for multi-time step. But before that, I would just like to tell, we already know that for in a day we have 24 hours. For each hour, the demand is fixed. If we take 1 hour, earlier it was 1 hour, in India now it is 15 minutes. So we have 15-minute time blocks. The market clearing happens each 15-minute time block. So for 15 minutes, the generation has to hold its generation. The schedule has to be maintained. Except for the ancillary services requirement, which may be there. In India, it is 15 minutes. For 24 hours, we'll be having 15 into 4, which is for one for each. For each hour, we have 4. And sorry, 24 hour, and in each hour we have 1 hour, 1 hour, we have 60 minutes. So four time blocks, 15 minutes each for 1 hour. For 24 hour, we will be having 96 time blocks. In US, it is 5 minutes. Every 5 minutes, we are doing the dispatch. Every 5 minutes. So for 20, it will be 24 into 5, that is 120 time blocks. For that, we need even faster formulations which give us a result very quick. Why do we need to go for multi-time shift? That we will see once we go to we are done with economic dispatch and we move on to the unit commitment part. Before moving on to different constraints, we will see why we need to consider different multiple time steps also. Let us discuss this economic dispatch using dynamic programming. Before that, we'll start with this problem for understanding the economic dispatch using dynamic programming. We will start with this problem. It's a very good problem, similar to what we have seen in the lecture notes. It's a similar problem. Only thing is, first of all, yes, this, what is the advantage of using economic dispatch? So dynamic programming for solving economic dispatch, we have seen different methods, right? Why do we need to go for dynamic programming? Because all these methods which we have seen, the equal incremental cost, that uses the lambda iteration method, which uses this principle of equal incremental cost. In that case, if we use equal incremental cost, let's say we have three cost characteristics, incremental cost characteristics. The equal incremental cost characteristics means these three. If all these three are marginal, they are not at their minimum maximum limit, then all three will participate in economic dispatch and we will get one solution. This kind of equal incremental cost is possible when this incremental cost characteristics is linear, right? It is convex. But if it is non-convex, then what can happen for a single incremental cost? There can be two values. Let's say here we can see this is a jump here. Here we can see for 60 megawatt, or it can be 40. We have two incremental cost here for one value because of the discontinuity. In such a case, we cannot use that equal incremental. And all this Newton method, all those things, they will also not work if there are discontinuities. If all those are applicable for continuous functions, if there is discontinuity, then we will not be able to use it. So for non-convex, or let's say it can also be like this. It can also be something uh, like this. Okay. Then here we can see for same incremental cost. we have multiple generation values. See, this is a non-convex function. We have three values. Which one to choose? In such a case, the previous methods which we have used may not work, will not work. In these cases, we need to go for, or we can use dynamic programming offers a solution for these types of problems. Here we can see, so we'll see this example. This example I have already discussed. These type of cost curves can be possible, and these are non-convex. Here, see, we have already studied, or we know that non-convex means a function is non-convex if you draw a line between any 2 points on that function, and if that line is not always above that function, then it is non-convex. Here we can see, although this line is above the function between these two values, but here it is below. So this line is not always above the function. Therefore, this function is non-convex, and in such cases, we cannot use the previous methods. Dynamic programming comes to our rescue in such a case. And that's why we are going to see dynamic programming. But one disadvantage of this dynamic programming or this economic dispatch problem in its nascent or its primitive form or simple form, where we have not considered any kind of time coupling, is that it leads to poor control of generators, poor control performance of generators. That we will see further. But now the most important thing to remember right now here is that the previous methods will not work if the cost function is non-convex. And therefore we can use dynamic programming. Now here we will see, this is not same example, it is similar example which we have seen in the lecture notes, but it is one of the problem study the pack of the Wood and Wallenberg book. Wood and Wallenberg book. It's a unsolved problem. You can see same problem I have picked up, and we are going to solve it. The problem is, this is a question that solve the economic dispatch problem using dynamic programming for a total demand of 210 megawatts, assuming that all the units are online. All the units are online, that all of them are available, they are synchronized, they are available and ready to connected to the network and ready to deliver power. In dynamic programming, one thing that we have to do, that we have to assume dynamic programming requires, although we want to solve, we need solution for 210 megawatts, but it will solve for all the demand in discrete steps. For dynamic program, we need to discretize the our cost function. Here, that's why it is said that we have to assume that there are discrete load steps of 20 megawatt. Here we can see the profile, the cost curves of these are heat rate curves, heat rate characteristics, and their unit will be, what will be the unit? MBTU per hour. Okay, MBTU per hour, and when we multiply it, the heat rate characteristics multiplied by the fuel cost, this is MBTU per hour, and if you multiply it by dollar per MBTU, then we will get our cost curve, dollar per hour. Input output cost curve. if just multiply everything by 1.5 and then we'll get the actual curve, input output curve. Here we can see that all the three generators, their maximum limit is 100, but they follow between their minimum and maximum. All of them have a minimum of 20 megawatts and a maximum generation capacity of 100 megawatts. But in between, they behave differently. It's not that there is a single quadratic cost curve, but there is one step in between. For generator 1, it is at 60 megawatt, for 2, it's at 40, and for third, it is at 50 megawatt. So in between, they have different characteristics, and we will see the graph in the next slide. How do they look like? Here, if we see the first one, it is almost, this is 60 megawatts. It is almost quadratic from between its minimum and maximum value. There is not much change. Only thing is the slope of this curve is changing between 20 and 60 the slope is different, and between 60 to 100 the slope is different. That's why here we'll see there is a division between 60 and after 60, here 40 and next 50. In case of this one up to 60, this is the slope, and then after 60 this is the slope. Okay, here you see for same generation we have two different incremental cost. This is a challenge, one of the challenge. And here if we see for 2, we can clearly see here the cost curve is discontinuous. It is continuous, but you can see it is non-convex now. If we connect the curve, if we draw a line, then the curve is non-convex. Here, this is a non-convex curve. This is a non-convex curve, and this is clearly a non-convex curve. Okay, these two are a little bit uh, slope was increasing, then it was again increasing. Okay, in both the cases, slope is continuously increasing, except this, the point of uh, discontinuity. Third one is very interesting. If you see here, the slope was increasing, but suddenly it has reduced, and then again it is increasing. There is a small mistake which I have done. I will rectify it. Just by seeing this graph, I have come to know that this is 60. Here the point of interchange is 40, and here it is 50. But for all these three, I have taken it as 60. It should have been 40. Change should have happened here at 40, and this should have happened at 50. That I will change it. I will update it. However, still the curve, you can clearly see the main thing which I wanted to tell you is that the three units are behaving differently, but although they have same minimum and maximum limits, they are behaving quite differently between their minimum and maximum limit. And also we have seen the non-convex nature, non-convexity here. These things are important to note here. I will change this one 50 and 40 and 50 and then update the results. The results will change a little bit, but not significantly. But the procedure will remain same. After doing this kind of plotting, even plotting is not required. It was just to show that yes, these are unconvex characteristics. And decision making is going to be difficult and previous used methods will not work. You can clearly see for a lambda of incremental cost of 25, we have three different value of generation. Which one to choose now? So it's an interesting problem. What we can do here is now we have considered that in the question we have been asked to consider discrete load steps of 20 megawatts. For each generator, minimum is 20 and maximum is 100. We can consider these points at a step of 20, 20, 40, 60, 80, and 100. 5 points for each of the generators. And for each of these points, we can calculate the cost. Okay. We can calculate the cost. I think only this graph is different. These calculations will not change. Okay. These are not going to change. These will remain same. Something might change. Only for this one it will change. For 40 I have used this, but I should have used this. So something will change, okay, but not much. Here we can see F2, it is 256. It should not be 2, it should be more than 424. Okay, that will change. But here you can see you can calculate F1, the cost of generation for each of these 5 points, 20 minimum, maximum, and in between 3 points. For 100, if we see maximum, this is the maximum generation possible for each of the generator or units. And cost is this. If we divide it by 100, then we will get the full load average cost rate. We will get full load average cost rate. And if we compare the three generators, then unit 1 is cheaper than unit 2, and unit 2 is cheaper than unit 3. This will not change. Now, what we have to do, we have to construct a table. We can do it without that also, but by constructing a table in a tabular form, it becomes easier to visualize things. Now we will see here. I have solved that problem. What we can do is F2, the function, overall cost function F will be F1 plus F2 plus F3. Okay. F1, P1, P2, and P3. And we know that P1 plus P2 plus P3 is demand. This one I can write. The stage 1 is P1, stage 2 I can write P1 plus P2. and CH3 is P3. P1 plus P2 plus P3. So for stage 1, for not stage 1, if this is 0 stage, then cost is F1 P1. For stage 1, cost is P2 minus T. D minus V2. Here you can see here. So stage 0, we have cost as F1 P1. And F1 P1. F1 P1 we have how many values? 20, we have 40, 60, 80 and 100. These are the possible combinations. And for stage 2, now F2 is F2 P2 cost of production by generator 2 plus cost of production from first generator. So first generator can be written it like this. So first generator P1 can be written like, it can be written as D minus P2. And what will be D here? Because P1 will P2 P1 is between 20 and 100, P2 is also between 20 and 100. But demand can be between 40 and 200. This can be demand, right? If this is P2, then P1 will be demand minus P2. Okay. Now we will see what we will do. This is our demand. And this is F1D, cost of meeting that. This actually this is F1 and P1, F1 P1. For first cost for first generator if it is producing this D. Okay, so it is, let's say it is F1D. And this is P2. P2, all these generator we have seen, they vary from 20 to 100 at a time at a load step of 20 megawatt. Therefore, P2 is 20, 40, 60, 80 and 100 here. And we can calculate the price also, the cost using the cost function. Up to 40 we have seen for P2. Up to 40 you can use this curve, multiply this by 1.5. And above from 40 to 100 you can use this one second one by multiplying it by 1.5 first. Then you will get all these values, okay, for each of these load steps. Now we have to see if for satisfying this demand 0. Demand 0 cannot be met. That's why the cost is infinity. It is not possible. Sorry, let me just drink. Have a sip of water. Demand 0 cannot be met because minimum of P1 is 20 megawatt, minimum of P2 is also 20. Minimum together they can generate 40. They can supply demand of 40, not below that. and beyond 200 also they cannot supply. This column shows what generator P1 can supply and at what cost. What will be the cost of providing that, supplying that demand. Here P1, if it generates 20, it will cost this much, and 100 will cost this much. Now, for 20 megawatt, what are the possible combination? There is only one combination, because both of them have minimum they can supply 20. If P1 is supplying 20, P2 has to be 0. It cannot be 0. It has to be minimum 20. It cannot supply. Only P1 will be on. P2 cannot be on in that case. That's why cost is infinite. But this combination is not possible. 20 for 20 only P1 will supply. Okay. Here it should have been 249.6. But because P2 is not possible here, that's why I have not considered this one. We will start from 40. Now 40, there is only one combination possible, because both of them has to be minimum 2020. Minimum they have to supply that much. If P2 is 20, cost is 256. If P2 is 20, then P1 has to be 20. For P1 is equals to 20, cost is this. Now if we add these two, we will get this. Yeah, 505.6. This is one option. Other option is entirely, so here P1 is 0. P1 will not, P2 is not even generating anything. Here cost is 249.6. It is not generating anything. It is off. Here we have two combination for 40. So for 40, let's say this is P1, this is P2. And for demand of 40, P1 is 40, 0, 20, 20. These are the two combinations. For 2020, the cost is this much, 505.6. And for 40, 0, the cost is 438.4. Again, I have made a mistake here, right? This is the minimum. Out of these two, we want to find out the minimum one. This is the minimum that P1 generate everything. This should be 438.40, and P1 is still 0. P2 is still 0 here. Now we move to 60. For 60, we have three combinations possible, right? First one is everything is generated by P1 itself. P1 itself. Then cost is 646.4. I will update this one. Second option is P2 generates 20 and P1 generates 40. In that case, you have to add these two. Add this one and this one. You will get this one. Third option is P2 generates 40 and P1 generates only 20. Then add this and this. We get this. Out of these three, which one is minimum? This one is minimum, 646.4. So this will be 646.4 and P2 is still 0. Now we move on to 80. If we see 80, then in 80 what is happening? One is either everything is generated by P1 itself. P1 itself. And the cost is 916.4. Second option is P2 is 20, P1 reduces to 60. Add these two values. This 256 plus 4, 646.4. You will get this. Second option is, here we have four options. Second option is P2 is 40 and P1 is 40. Add these two values. 424 and 438.4. You will get 864.4. And last option is P2 is 60 and P1 is 20. This 246.9. Add 246.9 and 657.32. Out of these four combination, this one is the minimum. Here this was the minimum. Here this is the minimum. And P2 is 40. Okay. Move on to 100. If we see 100, one option is entire 100 by P1. Second option is P2 provides 20 and rest 80 by P1. Add this to 256 and you will get this. Third option is P2 is 40 and P1 is 80. P1 is 60. Add these two, we'll get this. Then P2 60, add this to 40, P1 40 cost. This and this cost will get 109. Last is P2 is 80, add this cost, P1 is 20. You will get this. Out of all these five combination, minimum is this one, P2 is 40. So we choose this one. If you move to 120, then P1 cannot be more than 100. If P2 is 20, P1 has to be 100. Add this to 256, you will get 1502. If P2 is 40, then P1 has to reduce to 80, this one. Add this to this. Okay, now P2 is 60, reduce further it to by 20. It will also be 60. If P2 is 80, then it has to be 40 only to make it 120. And if P2 is 100, then P1 has to be only 20. Add this and this. These are the possible five combinations out of which P2 is equal to 60 is the minimum. Similarly, we can do it for 140, 60, 180 and 200. For 140, if P2 is 40, it is 100. If P2 is 60, P1 is 80. If P2 is 80, P1 is 60. And if P2 is 100, P1 is 40. And in this we find this is the minimum cost when P2 is 60. Similarly, when P2 for 160 demand, if P2 is 60, P1 is 100. When P2 is 80, P1 is also 80. And P2 is 100, P1 is 60. For these combination, this one is the minimum. For 180, if P2 is 80, P1 is 100. And if P2 is 100, P1 is 80. Last one is both are 100 maximum demand. These are the different minimum combination values possible. This has to be 0, 0 and 0. Now we have to record these. These are the combinations possible for first two units, so unit 1 and unit 2. These are all the combination demand which can be met. 20 is possible only when this should be 2496.6. 249.6. P2 is 0 here. 40, 60, then P2 is like this. For 100, both are 100. Okay. Now we have to move to the next stage where we have to add the unit 3. Now if we add unit 3, then what we are getting here? We know F2 we have already calculated. F3, P3. P3, if it is something, then P2, P1 plus P2 will be demand minus P3. Now, our question was we need to calculate the economic dispatch for a demand of 210. Because we already know all these combination possible values we know, directly we can calculate and this is the last stage, so we can directly calculate because the demand is increasing in the step of 20 and all the generators have these step 20, 40, 60, 80 and only 100. The overall demand which can be satisfied will also range from 20 to 300 at a step of 20. So we can see that the demands which can be met are 200, 220, 240, 180 like this. The demand in between, which is 210, cannot be met, can be met, but we don't know the values for that. So we need to interpolate for that. We can calculate what is the cost for 200 and 220, and in between we can interpolate. Same thing we are going to do here. First we will calculate it for 200, then for 220, and in between we are going to calculate what is the cost. And also by seeing the cost and the generation schedule for these two values 200 and 220, we can know what will be the generation cost as well as schedule for 210 value. This we want to know. It's a very important step. First thing is right from this step, if we move, when we are given this heat rate, first multiply it by fuel cost, then you will get the overall cost. Okay, then calculate, because we are using dynamic programming, it requires discrete steps. We are taking here discrete step of 20. Therefore, for each generator, we minimum to maximum with a step of 20. We get total 5 steps. 3 additional steps excluding the minimum and maximum values. These are those 3 steps. We get 5 steps, and for all these 5 steps, we can calculate the cost. But if you want to know what is the cost for generation in between these steps, then we can interpolate. Same thing we are doing here. We have calculated all the combination for first 2 units and all the possible demands which can be met at what cost and what will be the optimal generation also that we have found. Now we want to see how 3 units will supply a demand of 210. For that we have already calculated it for 2 units. We need to add one more unit, which is a unit 3, which we are going to add now. For these 2 demand values, we want to know 210 to 200 and 220. Because 210 lies in between, we need to calculate the generation mix as well as cost for these 2 load levels. Now, if P3 is 20, then P1 plus P2 has to be 200 to meet because demand is 200. So P1 and P2, P1 plus P2 has to be demand minus P3, which is 180. The cost for P3 is equals to 20 is this, and for P1 plus P2 is equals to 180 is this. 2203.71 plus 246. You will get this 2450.37. This is the one combination possible. Second combination is P3 is 40 and P1 plus P2 is 160. 160, the cost is here. Add these two values, 500 and this, you will get 2373. Increase P3 further by a step of 20. Then it is 60, P3 is 60. And so P1 plus P2 will be 140, 200 minus 60, 140. And 140, the cost is. Then add these two values, 796.66 and 1573.72. You will get this. Now move on to 80. If P3 is 80, then P1 plus P2 has to be 200 minus 80, which is 120. The cost is this. Add these two costs, 1303.72 plus 1116.7. Cost is this. Finally, if P3 is 100, then P1 plus P2 has to be 100. And need to add the cost 1070.40 plus 25 plus 1516.7. We'll get this. Out of these 5 combination, select the minimum one. This is the minimum. This is the combination which is rendering minimum cost of generation. We come to a conclusion that P3, optimal value for P3 has to be 60 and P1 plus P2 has to be 140. And we can go to this table. From here we can find out that for 140 P2 has to be 60. So if P3 is 60, P2 is 60, then the remaining has to be generated by P1. 160 plus 60, 120, 200 minus 120 is 80. P1 has to generate 80. Similarly, we have to do it for 220 also. It's a small system, that's why we are able to do it manually, but otherwise we need to write code for this. Okay. Now 30 for 220. P3 is 20 here. P3 is 20. Remaining P1 plus P2 has to be 200. So add this cost 2570.40 plus 246.66. Then we get this cost. Similarly, we can do it for 40, 60, 80, and 100. If P3 is 40, then P1 plus P2 has to 180. Add this and 500. If P3 is 60, then P1 plus P2 has to be 160. Add this cost and this cost. If P3 is 80, add this cost, and then P1 plus P2 has to be 140 at this cost. If P3 is 100, then P1 plus P2 has to be 120 at this cost, 1303 and 1516. Out of these 5 combination, minimum is this. P3 is 60. For both these two, P3 is 60 and P1. If P3 is 60, then P1 plus P2 has to be how much? 160. If we go to 160, we see that P2 is 80. P2 is 80. Now these two are known. 140. 140 minus 220 is 80. P1 comes out to be 80. Here, if we see for these two cost demand levels, P1 and P3 are not changing. They are fixed. Okay. Only generator which is changing is P2. P2 here is a marginal generator. P2 here is a marginal generator. We can directly know because P1 is remaining same. Even for in between values also P1 and P3 will remain same. For a demand level of 210 megawatt, we can safely conclude that P1 will be 80 megawatts, P3 will be 60 megawatts, and remaining will be served by the 140, 60, so 70 megawatt by P2. And we also know the cost for this directly from their cost curve 80 and 60. Here we have already calculated. For P1 is equals to 80, this 916.4, hence this is 796.66. And here you can see 916.4 and 796.66 for this is for P1 and this is for P3. For P2 we need to calculate using this interpolation mechanism, because we know that P2 is this. At 60 it is 657.32. At 80 it is 957.3. In between we need to calculate. You can use straight line equation and calculate the value. The cost comes out to be this 807.32. Now we can sum all these three to get the overall cost of generation. If this was the economic dispatch using dynamic programming through an example, which was with non-convex non-convex input output characteristics. Now the problem here, what we have done, we have seen that we have calculated this for a single demand value. Let's say this is for at time t is equals to 12:05, not 05, let's say 15-minute interval PM. Okay, afternoon, 12:15. This is the demand. Okay, as per this, we are going to calculate economic dispatch for each time block separately. Let us assume that the so this is 280. Okay. Let us assume that this was the economic for this one economic dispatch we have already calculated at 12:15. This was the load requirement, and P1 comes out to be 80, P2 comes out to be 70, and P3 comes out to be 60. Now let's say we are moving to the next time step, and there the load requirement has increased by 70 megawatts. Now the generation needs to increase. Although we have not calculated it, but I think we can calculate. Let us calculate it. What we are saying, what is the demand here? 280 megawatts. Let us calculate it for 280 megawatts. Okay. P3 is 20 here. If P3 is 20, then P1 plus P2 has to be how much? 200. No. So P1 plus P2 is maximum 200. P3 has to be 80 here in case 80. So there are only two combinations possible here. One is P3 is, for this we have two combinations. One is P1 plus P2 is 200 and P3 is 80. P1, P2, and this is P3. Next is P1 plus P2 is 180 and P3 is 100. In both cases we can meet 280, right? In this case, we need to add 116.7 plus 200 is this 2570.4. Let me just add these two values. What is this? 116.7 plus 2570.40. This comes out to be 3687.10, and then last one is 80 and 120. Now what we have to add here? Here we need to add, this is no, sorry. Here this was 2570.40, plus for 80 it was 116.7. Here it is 2203.71 plus 1516.70. 2203.71 plus 1516.70. This is 3720.41. This is the minimum cost, 3687.10, and P3 comes out to be 80 here. Okay. Now I was saying this. Here what is the optimal? This is the optimal. Okay. P1 is going from 80 to 100. P2 is going from 70 to 100. And P3 is going from 60 to 100. This is schedule as per the individual economic dispatches for two different time blocks or the successive time blocks. This is the optimal as per economics. Optimal for this time blocks as per the economics. I mean, this will give us the minimum cost solution. However, to meet this solution, what will the AGC do? These three generators, if they are connected to the automatic generation control, then what it will say that please increase your generation, because there is an increase of load of 70 megawatt, which is divided as 20, 30 and 20 between these three generators P1, P2, P3. AGC will signal these generator to increase their generation by these three values respectively. Okay. Now, although these solutions are economical, these are economical, and AGC want them to, the control requires this much change. But there is a problem that the generators, thermal generators or thermal units, they have a maximum prescribed ramp rate limit. That is how much these generators can increase or decrease their generation or output every minute. This is generally given in, it's a rate, how much it can change per minute, megawatt per minute. For each minute, how much generation output the generator can change. It can be 1 megawatt per minute. Let us assume that this is 1 megawatt per unit. Okay. Or let's say it is 2 megawatts per minute. Okay. Now, if it is 2 megawatts per minute, then what will happen? This means that 30 megawatt per minute of change is possible. Sorry, not per minute, per 15 minutes. That is per time block. And we are moving from 12:15 to 12:30 p.m. That is a change of one time block. And the generator can increase its output by only 30 megawatt, maximum by 30 megawatts. It can be, so we can say that P1, and this is at, let's say this is time block T1, this is time block T2. So P1 at T1. We want this P2 at T1, sorry, P1 at T2 minus P1 at T1, because T2 is we are increasing, and this difference has to be less than 30 megawatts. Now if we see what is P1 at T2, it is 100 megawatts. What is P1 at T1? It is 80 megawatts, which is 20. And this is less than equals to 30 megawatts. So this is satisfying the ramp constraint. Satisfied. Similarly, if we check it for other two generators, let us say P2 T2 minus P2 T1. What is this? It is 100 minus 70, which is less than equals to 30. It is almost exactly 30. Similarly, for P3 also it is satisfied. Okay, let's say this is only this is 1.5 megawatt per minute. Then for 15 minute, how much it will be? 15 into 15, it will be 22.5 megawatt per time block. Okay, in this case, what will happen? This is 20, this is 30, and this is 22.5. Satisfied. However, this one will not be, even if we take a ramp limit of 1.5 megawatt per minute, then P1 and P3, because their change delta P, which is Pi T2 minus Pi T1, which is delta P is less than equals to 30, because for both the generator it is 20 megawatt, which is less than 22.5. But for generator 3, generator 2, T2 minus P T1 is, it is 30, and it is not less than equals to 22.5. Here it is violated. Although the economical solution, the optimal solution as per the economics, it says that the generator 2 should increase its generation by 30 megawatts, but the practical limit, the control of the generator doesn't allow that. So even if we go by the optimal solution, the economical solution, the control will be violated, the ramp limit will be violated, which cannot be allowed. So what is the solution? Therefore, I was saying that economic dispatch also need to be done multi-time step wise, not considering only a single time step, because that way we are violating the technical constraint of thermal generator. Same thing is written here for the large. This should be large. For large generators, the output cannot, the large generators cannot change their output above a prescribed maximum limit. Similarly, here we have seen that the output is increasing, the load is increasing. Same is also applicable when the load is reducing. Suppose if the load was reduced, let us say here we are saying P1 T1 minus P1 T2. Okay, we are saying T1. This is delta P1. Okay, and we are saying that delta P has to be between delta P max and delta P minimum. Sorry, minus delta P max. Okay. Now, earlier this was 100 and this was 70. Now I am saying instead of increasing generator, we are reducing it by 30. Let's say this was initially. This was increase in load. This is for increase in load. Now I am decreasing the load by same amount, 30, decrease in load. Considering 1.5 megawatt per minute ramp limit. Now I'm decreasing the load. Here the change is right now 40 minus 70. This is minus 30. And this should be greater than equals to minus 22.5. And minus 30 is less than minus 22.5. This constraint is violated. So both ways it should be satisfied. Okay. So what is the solution? How can we overcome this? We can easily overcome this by incorporating what we can do. Solution. Solution is two step. One is first make it make ED problem from single time step to multi time step for the entire day. Do it for the entire day. Second, incorporate the ramp rate constraints into the ED formulation itself. Ramp rate constraints. Incorporate these ramp rate constraints into the economic dispatch formulation, or we would say multi-time step economic dispatch formulation, this one, this modified one. And we can easily see, now you can see the formulation here. We will have one more additional constraint in addition to the one we already have. This one is the without ramp rate. We have already seen this. If I remove this part, okay, we consider only one summation. Then this is our single time step economic dispatch problem subject to these constraints. Okay. Similarly, this time will also change this or remove this t. If you remove this time component, then it is a single time step problem. But we have already seen that we cannot solve this problem individually because of this coupling constraint. These constraints are called coupling constraints. We see these constraints for for these ramp rate for generators, for storage also. We'll see that for energy storage. We have already discussed one kind of energy storage, which was the pumped hydro energy storage. There are SOC update equations or energy update equations. So energy at t plus 1 is equals to energy at t plus some charging into delta t minus discharging into delta t. Considering that efficiency is 100%. If efficiency is not 100%, then the efficiency term will also be there. Here it will be this efficiency term will come in picture then in case. Okay, here also we see it is a time coupling. All these are time coupling. We cannot do to ensure all these things, we need to do multi-time step economic dispatch, and which we are doing here. Now we have two summations, one for each generator, for all generator, cost of all generator for all the time periods, time blocks. Let's say we have 24 or let's say 96 time blocks, 96 time blocks. Then this capital T is 96 and let's say 3 generators and N is 3. I is 1 to N 3 and T is equals to 1 to 96. Fi PIT. And subject to this power balance constraint here, and this has to be satisfied for all time block from for all T is equals to 1 to for T is equals to 1 to T. For each time, this constraint need to be satisfied, because this PLT, which is load, this is demand. This is a time series, some a typical load profile, something like this. Or it's maybe have evening peak. We have like this, something like this. This is time here. This is 1 to 96. This PLT for each time block, or we can say PL is a vector of 96 cross 1. If PLT is one of the elements of that vector. For each time block, we need to satisfy this. For each time block, at each time block, the load is equals to the summation of all the generators. And then generation for each time block for each generator has to be, this is to be satisfied for each I is equals to each generator and for each time block, because the generation has to be between its minimum and maximum limit. This is without ramp rate. Now if we add the ramp rate, what will change? The objective function is going to remain the same. We are going to add one more constraint which we have already discussed, that the successive time block, the generation change is limited by the ramp rate. Decrease or increase, both are limited. That we need to incorporate. Here we can see these two constraints remain same, and the change is here. And we already see that we have already seen that pi t plus 1 minus pi t is equals to delta p. And this delta p, we saw that we have said that it should lie between delta p max minus delta p max to delta p max. Okay, this is the ramp constraint. I hope it is clear now that single time step ED is not a practical solution. We need to consider all the time steps. The time coupling needs to be taken into account. And second one, yeah, that was the one. That needs to be taken into account. Now we move on to the unit commitment part. And we will see what is the difference between economic dispatch and unit commitment. In unit commitment, we are saying that all the generators are available. Okay. Yeah, unit commitment. Now, commitment means that a unit or turned on is that unit we have to bring a generator to its feed, synchronize it, and connect it to the network to make it ready for supplying the demand or meeting the demand. Now, the economic solution, if we have, let's say we have 10 generators, okay, with a say minimum capacity, they're together, their minimum capacity is, let's say, 500 megawatt, and their maximum capacity is 1200 megawatts. Together, their aggregate minimum and maximum generation capacity is this. And over a day, we all know that, as I have already drawn the load profile before, the load is not constant. It is always changing throughout the day. It is not constant. Let us say that this is the load profile and this minimum value is, let's say it is 450 megawatts, which is less than the minimum. That means that the generator can satisfy, because even if all the 10 generators are on, these can satisfy the demand. However, if the demand is 550, let us say if the demand is 450 megawatt, which is less than the P summation of minimum generators. So generation is more than demand. This is a feasible solution. This is possible. One of the it can be done. One of the combination, as we have seen in the dynamic programming. There can be several combination to satisfy this demand. This is one of the combination that all the generator are running at their minimum value. Suppose the demand is 550 megawatt, but this is greater than their minimum, P minimum. If all the generators are at their minimum, then we cannot supply the demand. But we can easily increase because we know that the total generation has to be between this. And if demand is this much, we can satisfy. We can satisfy the demand. The sum of the generator can increase, go beyond their minimum value. Okay, so point is that if the demand is more than the technical minimum, then demand cannot be satisfied. If all the generators they are made to run at their minimum level, that combination will not work. It will be an infeasible combination. Okay. Now I was saying that the load is changing always. Okay. Here, let's say we are saying all the generators are on and they are at their minimum value here at this point. But this is the peak load. Let's say this is around 1150 megawatt, and this requires all the generators to be on. Now, in between this is a difference of 700 megawatts. If all the generators are kept on, they are synchronized, they are committed, but they are not generating. Although the generators are not generating, but to be committed, to be synchronized, they need to maintain their temperature operate the temperature level so that whenever required they can generate. So maintaining that optimal temperature also requires cost. It entails cost. If so that's why it's written here. It's expensive to commit enough generator and keep them online. If we can decommit some generator, we can off some generators and make them online when required. Let's say in between this period, I can switch off certain generators. Maybe I can switch off some generators here and then switch on here instead of keeping them online in between. Then I need to compare the cost for these two operations, C1 and C2. C2 where I keep them online, what is the cost? C1 where I make them offline and supply the demand with the other generators. Compare the cost. Which one is better? Which one is more economical? We will go with that. This kind of analysis is done using unit commitment. Here we are allowing the generators to go off, to generate nothing. Either they are zero, they generate nothing, or when they generate, when they are on, they have to generate at least P minimum if they are on. Zero or P minimum. Okay. If we consider ED only and let's say minimum is 500, total minimum and demand is also 500, then ED would say because we have a constraint that all the generator need to run at least because they are on, and there is a constraint that Pi should be between P minimum and P max, and all the generators are on, then all the generators need to be at P min as per ED. But if I am allowed to do such kind of business, then I can make it is possible that one of the generator which is cheapest is 600 megawatt rating, and that unit alone can satisfy this entire 500 megawatt demand. Then I can use only one generator, and rest nine of the generators are off. Or maybe two, three generators are sufficient to meet this demand of 500. Why to keep other generators on if it is more economical? Okay. So this is the motivation for doing unit commitment, that if it is more economical to switch off certain generators and bring them on whenever required, then why not do that? Finally, our aim is to satisfy the technical constraint as well as do it economically. If both can be done, then it's a win-win situation. Therefore, unit commitment comes into picture. So if they are expensive, the solution is to decommit them when not needed and bring them online when they are required, with the aim that overall cost is still less as compared to when they were kept online. Okay. Now here challenges that they result into binary variables, as I've already said, that in ED all the generators are on, so they will have to be at least at P minimum. Now we are saying that it can be zero also. It can be zero, and if it is on, then it has to be at least P minimum. Then so we are saying introducing binary variables here, integer variables. Now, so these are the differences between economic dispatch and unit commitment. We already seen that in economic dispatch, here the assumption is that all the n generators are already connected. They are all committed. If you will say here, economic dispatch would say that unit commitment with there is only one. If three generators are there, then for three generator, how many combinations are possible? 8 combinations are possible. Sorry, 7 combinations are possible because 00 is off, is not allowed. 7 combinations are possible. Okay. N generators are already connected. Here, overall 7 out of this, economic dispatch would say there is out of these 7, only one. Economic dispatch is pertaining to that only one solution, which is one combination, which is this, that all the generators are already connected. They are committed. And the purpose is to find out the optimum operating policy for all the connected generators. Unit commitment, on the other hand, says that not all of them may be necessarily required. We may decommit some of them. So out of these 7 combinations, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Out of these 7, okay, let me write it again. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the 7 combinations. 1, 2. Economic dispatch is this one, considering that all of the 3 generators are on. Unit commitment, on the other hand, will look for all these subsets of the complete set. So these out of 7, which one is economical? It may be possible that, as we have seen in previous example, that only using one generator might be sufficient, and that might be more economical than using all the 3 together. And if using only one generator is more economical, then I will use only one of them. So here the purpose is which subset should be used to minimize the operating cost. And thus we can see the solution procedure involves ED as a subproblem. For economic dispatch, for unit commitment, economic dispatch is a subproblem. Let us say if unit commitment says that this combination is the most economical. And how would I know that? For each of these combination, I will have to do economic dispatch. So for unit commitment, I will do 7 economic dispatch, and out of these 7 economic dispatch, which one is least cost? Having the minimum dispatch cost will be the solution of unit commitment. Thus, the solution procedure of ED involves the UC involves ED as a subproblem. We will solve 7 economic dispatch problems for 1 unit commitment. And then the minimum of that, minimum of, let's say if FED is a problem, FEDI, where I is equals to 1 to 7. I lies between 1 to 7. And the minimum will be, this will be the solution of CUC. This is the difference between economic dispatch and unit commitment. Okay. Now unit commitment, the most simplest way is to use a brute force. You know that the load is changing. It is increasing and decreasing. What we can do that, here we are considering unit 1. We are considering all these 7 combination. We see that when only one unit is running, is committed, the maximum generation which can be with maximum demand which can be met is 100 megawatts. When 2 are online, then 200 megawatts can be supplied. And when all the 3 are on, maximum 300 can be supplied. So we can simply by seeing this, we can say that if when demand is more than 200 megawatt, say all the 3 generators are on. Unit 1 plus 2 plus 3. Together they will supply. When the demand is in between 100 and 200, in between 100 and 200, then I would say I would drop 1 unit. I will use only unit 1 and 2. I will drop unit 3. And if demand is less than 100 up to 100 megawatt, then I will use only unit 1. Unit 1, here we can see the average cost is minimum for unit 1. You can use cheaper. Here these 3 are having same maximum, that's why we are getting this. Otherwise these values change. So let us see if we are let us just wait. Okay, this we have written this brute force. We use this one. Let above this unit 1, 2, 3. For this unit 1 and 2. For this unit only unit 1. Now use this This simple brute force technique, or we also call this is a priority list. We can say this is a priority, or we can say this here, a shutdown rule, a simple shutdown rule. As the demand is reducing, we are shutting down the unit, and when increases, we again bring this unit back. For here now we can use, right? This is unit 1, unit 2, and unit 3. Okay. Let us make this table. For 260 megawatt, 260 megawatt is about 200. You see, all the 3 units are on. 220 is still above. All are on. 200 up to 200 unit 1 and 2 only. Okay, 3 is not here. Now 80 unit 1 and 2. 140 1 and 2. 100 up to 100 only 1, not this. 1 and 2 again, 1 and 2, 1 and 2. No third. 1 and 2. 3, all the 3 are. So this way we can use this. Unit commitment will result in this. So unit 1 is always on. We will say, if we draw this diagram, we'll say this is 100, this is 200, this is 300. Okay, so what is happening for all these values? Uh, 1, 2, 3, 6, 9, and 11. This is 1 to 11. And for each of this we can draw. We can say unit 1 is always on. We can plot it first. 260, 240. I don't have a plot here. It is something like this. And you see unit 1 is up to 100, unit 1 is always on. Unit 1 is always on. Unit 2 comes for 200. Only here up to 200 unit 2 will come. Then unit 3 will come only above 200. This will be unit 3. Unit 3. This is roughly I'm drawing. This is unit 2. Unit 2. This is unit 3. Unit 2, and this one is unit 1. So unit 2, 1, 2, 3 we can do it like this. This is the most basic way. Now moving on to unit commitment. This is a simple technique. And here we are not considering any kind of other constraint. The simplest constraint which we saw was a ramp constraint. This also we are not considering here, although we can do that in priority list. And in addition to ramp constraint, also there are other constraints which we will see here, which are tabulated here. You can see all the constraints. So many constraints are there. The primary constraint is that enough units are committed to supply the demand. Then there is spinning reserve constraint, that sum of the total synchronized unit, the generation from them, minus the load and losses. That will be spinning reserve. That also we need to maintain, because we need this one, because if one of the generator or the highest generator highest generator goes off. Then still, or one line goes out. One line goes out. One generator goes out. Or demand increases. And still we should be able to meet the demand. And that is possible by spinning reserve. They are committed, but they are not generating. Whenever any generator outages is there, line outage is there, these generator can be called up to generate. This constraint is very important for the network security. And reliable power supply. The next constraint is the minimum uptime constraint. Let's say a unit, these two constraints are important constraint, and their modeling is also is little bit difficult. They involve more binary variables to keep track of their on and off status and also startup and shutdown. The minimum uptime says that if a unit is on, let's say a unit is on at time t1, then if its minimum uptime means, let's say minimum uptime of a generator is 3 hours. And if it is on at T1, then it has to remain on for at least 3 hours. It cannot be off before that. From T1 to T2, T2 to T3 and T3 to T4. For 3 hours, it has to be on. Or if we consider it was on at 1 hour, so it has to be on for 3 hours. At least for 3 hours. It can be off after that, but before that, it cannot be. If minimum time is 3 hours. That is, it should not be turned off immediately. It has to satisfy. It should turn off only after the minimum hours. After being on for this measure. Similarly, downtime, if a unit is decommitted, if it is off, it should remain off. Remain off for T off for downtime. Should remain off for that much time, because if a unit is off, then to again start generation, it needs time to bring its temperature to that level. In this off condition also there are two types. For this, when a unit is off, then again bringing it off entails startup cost. You need to start it again, and it can be of two types. One is cooling and one is banking. And this is more costly. It also depends on the duration for which it is done. So cooling means the unit is completely cooled down and again it is brought back. While banking says it is not completely cooled down. It is few hours back it was just shut off, and still a minimum operating temperature is maintained. So to bring the unit back from banking will require less number of time, less hours. And after completely cooling, it will require a long time. several hours. And that's why it's a time dependent. Startup cost is time dependent. It is not time independent. It depends on how much, when the unit was off, how many hours back ago. Crew constraint requires that the number of personnel present in the plant are uh, only enough or sufficient to run only one unit, not more than that. That is also a constraint. So we may not be, although a plant might be having 3-4 units, but because the operating personnel, the persons who are working there, they are not sufficient to run the plant. Only one unit can be run. So that is also a constraint. Then hydro constraint is there. Some generators might be require to coordinate with thermal, to coordinate with hydro plant, and that for them separate hydrothermal scheduling coordination needs to be done. Then some units are must run because some units are used to even supply steam to industrial processes. In India, we generally winters are not that severe, but in European countries or American country, in America, the winters are quite extreme. Sub-zero temperatures are there for months together. And in that case, the heating requirement is quite high. So for domestic as well as industrial purposes, steam requirement is there. So apart from, there are few generators called as these cogeneration plants. They are required to not only generate the power, electricity, but also generate steam. In that case, to supply that steam requirement, those generators need to run. They will generate electricity as well as provide the steam. In that case, they have to run, must run. They are under must run category. Or even sometime for voltage support for the network, they might not be generating, or they might be generating only minimum, but they are still connected. Minimum only for supplying the voltage, or they will provide more reactive power support. Then fuel constraint, there will be sometimes we see that because we procure coal from outside. In India, the coal production is not at par with the consumption, the demand, the requirement. So we import coal from outside other countries. And sometimes if the coal availability is limited, then we need to uh, use only limited amount of coal. That also need to be taken into account. Although the requirement of demand is that is very high, but the due to limited amount of coal availability, I may not be able to generate that much. All these are different constraints which need to be satisfied. Here, I think I have missed out on the ramp constraint here. There are startup and shutdown rates also. These are different, but these are similar to the ramp rate, and but these are different. Their values are different from these ramp rate. UC method, we have already seen the brute force one, priority list. Here we have a simple shutdown rule. The problem with these two methods is that we have to see all these 2 raised power n minus 1 combination for each time block. Combinations for each time block, and if there are m time blocks, let's say, let us consider the same notation which we have used, t time blocks, then we will have to consider these many combination for the entire day. 2 is power n minus 1 to power t. So t will be here 96 for 96 time blocks. Very huge number of combination. So dynamic programming reduces this dimensionality of problem. Here we can consider only if we consider strict priority rule order. We will see in the next slide. Then Lagrange relaxation is the another method, improved version of not improved version, but it is a better method because dynamic programming also offers several limitations which we cannot model. All the constraints cannot be modeled using dynamic programming. It becomes quite complex, and because we will get the optimum value from dynamic programming only when we will use all these combinations. But using so many combinations become computationally challenging, so we reduce the number of combination by following strict priority order. In that case, all because the combinations have reduced, we may not reach the optimum. Although we may not be very far from the optimum, but still optimum is not achieved. And that problem is overcome by using Lagrange relaxation, which guarantees optimality. And this is one of the decomposition techniques. There are other decomposition techniques also, AD, MM, and other ones. Okay. Then other improved version, better version is MILP, which is the state of art nowadays. Mixed integer linear programming method. These let us move to the unit commitment using dynamic programming. Here, if we follow that, so the same thing which I was saying, if we consider all these combination, then dynamic programming also becomes computationally challenging. And we have already seen that there are 15-minute time block, and we need to solve this unit commitment quickly. Here, we need quick solution. We cannot wait for a day to solve for day ahead unit commitment problem. That's why time is crucial here. We cannot exercise all the for 1,000 generators. This combination is exponentially large. It is very huge, and we cannot do that. That's why, and if we reduce the combination, then we are away from optimality. That's why we, even for reduced combination, we use the strict priority order scheme. Here, for n combination of n unit, for here we will get only n combination for n unit system. If we have 3 units, we have already seen that. If we have 3 units, we have already seen that strict priority order here. Right? This one was the same strict priority order. U1, U3. We were saying that U1, that U1, then only U1 and U2, then only U1, U2, and U3. These are the only 3 combinations possible, we will say. 3 feasible combinations. Okay. So only 3 combinations for 3 unit system arranged in order of full load average cost rate. So here we have to see that the unit with the lowest full load average cost is U1, and U3 is the one with the highest. Here, this U1 is having the lowest full load average cost rate, and this is the highest. So U1 is this first one, 2, 3. First, the cheapest generator will be loaded. Then next cheapest will be coming. Then the most costliest will come when the demand is very high and cannot be met by the first 2 units. Okay. Let us move forward. Then forward, we already know that dynamic programming can be done forward or backward, and forward have these advantages we've already seen. And this is the forward dynamic algorithm. I think time is less today. If you have any doubt, you can ask me in the next class. Next class, we will discuss this. If you have any doubt, you can discuss this dynamic programming. We can discuss next class. Otherwise, otherwise we will see the Lagrange. This next week material is a continuation of that Lagrange relaxation method and MILP both. So both those 2 methods we will see in the next week, and those are very optimization specific methods. Yeah, very mathematically oriented. Dynamic programming is also one of the automation technique, but they are fully mathematical. Here we can see flowchart, but in yeah, we'll see that motivation. That is also very important. I will go through that. Maybe next class I will repeat the same thing. Let us see this flowchart itself first. I will motivation of Lagrange relaxation we will take in the next class. Here we start with the first K. Here is the time block or K stages T we can say, which is up to 1 to 96. For each time block we want to solve this, right? So F cost K is time block. Let's say first time block K start K is equal to 1, and I is the number of um, set of values. We have taken all the states in period K. So in period K we'll be having only one state because initial condition of the generator. If only three generators are there and initially only one second unit was running, this will be initial condition, that is only I here. And oh sorry, I will be here the three. If three generators are then three combination U1 U let's say 001 011 and 100, sorry, 0 and 111. These are the three combinations. So this is I, this is I, and L is here 1. And means 1 is one subset because based upon the initial condition. Let's say only second generator was running. Okay. So this is the production cost, and this is the transition cost. K minus 1, so which is for K is equal to 1, this is 0, this is 1, 0 to L. So this becomes S cost 0, L will be only, let's say here 0, 1, 0, and 1, comma. Here we have 3. I is this subset 3, 0, 0, 1, 0, 1, 0, and 1, 1, 1. These three values. So here we will get for each I we will get this F cost. Okay. From each L, which is 1 here. Means only one state here in the 0th stage. Or 0th period we can say, time period here. Because we have initial condition of this. But in subsequent time periods, this L subset will be having more than one values. And we will take only n feasible state. Out of 2 raised to power 3 minus 1 combinations, we are taking only 3. We will save only 3, store 3, 1. 3 feasible states in interval K minus 1. So K, now K becomes 2. And K minus 1 means 1, state 1. What are the feasible state? Out of them, we are taking only n feasible states. So L here can be out of these three, 0, 1, 0, 0, 0, 1, and 1, 1, 1. Out of these three, we are taking out of the 2 raised power minus 7 minus. Out of those, we are taking only these three feasible states. Okay. If we need to check either whether they are feasible or not. If some of them is infeasible, then discard them. Take only feasible ones. Then again continue. This will be the cost for the kth. So it will be 2 here, comma I, and it will be 1, comma L, K comma, is 2 comma I. And this is transition cost if there is some startup or any unit is on. Let's say initial condition was this, and this I is 111. One state is this, let's say, possible feasible state. Then there are two transition, two startup costs are involved here. Okay. And this is up to state k minus 1 f cost. We need to do this for all the states I in period k. Save the n lowest cost strategies and then do it till we reach all the periods and then trace the solution. This motivation we will discuss in the next class. And we'll take the question for economic dispatch that neglects line losses but includes generation limit. What should be done if power is outside the limit of a generator? We know that if the power is outside, if is less than P minimum or P is greater than P max, then in this case we say P is P minimum and P is P max. Make them equal to their minimum or maximum power. Okay. And that generator is no longer a participating generator in the optimization dispatch. Let's say there are 3 generators and out of them P1 is less than P1 minimum and P2 is greater than P2 max. Then this will be set at P1 minimum, this will be set at P2 maximum, and remaining the third one will be P3, remaining power. Or if we take only one of them reaching its minimum limit, then the optimization, it will be out of optimization and remaining we will do optimization for the remaining two. This will be set at its minimum and then optimization will be done only for the remaining two generators. Techniques for solving unit commitment, this we have already discussed. Priority list, dynamic method, Lagrange, and MILP. Kuhn-Tucker is not a method. These are conditions for optimality. Then next is, what are the thermal unit constraints? What are the thermal unit constraints? Minimum uptime, minimum downtime, and crew constraint, not maximum. Minimum downtime constraints entails that the unit should come up. Unit cannot come up immediately. Downtime means if it is off, then it should remain off. Remain off for downtime hours. Spinning reserve, yeah, it should be a given percentage of forecasted peak load. And it should be capable of making up loss of most heavily loaded unit. It should be spread out and sufficient for making a failure of any generating unit failure. So it is, all these are correct option. In strict priority order scheme, we have seen only n combinations for a n unit system, and which are arranged in the order of full load average cost, not minimum load. They are not arranged randomly. So first and two are correct. Forward dynamic program, it cannot handle, it is incorrect. It can handle. Initial condition are easier to satisfy, so this is also not correct. Computation cannot go forward in, it can go forward. This is also, all are incorrect in this case. Two types of startup cost, cooling and banking, which we have already discussed. The cooling is to boil, sorry, it is cool down. Cool down the boiler and then heat it back up to operating temperature in time for a scheduled turn on. Banking, to provide enough fuel to supply sufficient energy to just maintain the operating temperature. Yeah, so today's questions are over. We will stop here today. Thank you for joining everyone, and we will see See you next class. We will discuss the next week Lagrange relaxation as well as MILP. Thank you very much.